My name is Archer Gill. Welcome to my data science project. So the goal of my project is to be able to predict the closing price of the S&P 500 stock market index. And I'm going to use a linear model. I got my data from Log5 Statistics, which we talked a little bit about in class. So the reason that I chose this project is I love stocks. I check my stocks every day. I've been trading since I was 14 years old. I started with $5 in my dad's name, and I haven't looked back. I trade every day. I love the idea that you can literally do nothing and get free money. So that's why I love stocks and what led me to choose this project. I also thought that stocks are very math based. It's all numbers, it's all math, so they really lend themselves to analysis. This project is like a great kind of entry point. There's a lot of places I could go from here, kind of just to get me interested and just mess with the numbers a little bit. Yeah. So I thought I'd explain some of the variables and some of the terminology that I'm going to be using just so that it's more meaningful. So the S&P 500 index it's a stock, and it's the average of the top 500 companies in the world stock. So it doesn't really fluctuate because it's an average of 500 different stocks, and it generally just goes up very slowly. So people like it for that reason. It's just a secure, reliable, doesn't move much. It's an average. It's one stock representing 500 stocks. So volume, basically how many shares are being traded in a given time period. It's an indicator of how much people care about the stock, good or bad. If a stock is in the news, it's probably going to have high volume. If it's something like Blockbuster Video, it's probably going to have low volume. It's just a measure of how much the stock is being traded. So the high and the low are pretty self-explanatory. It's just the highest and the lowest price that a stock will hit during a given time period. My project is in days, so it's the high and the low for the day. And that goes for the volume too. Opening and closing price are also pretty self-explanatory. It's just the price of the stock when the market opens and when the market closes. If you didn't know, the market opens and closes. It opens at 8:30 in the morning in our time zone, and it closes at 3. So yeah, and like I said, it's all in days. So all this is measured day by day. So like I was just saying, these are my variables. What I'm trying to predict is the closing price, and I'm going to do that using the opening price, the high, the low, and the volume. So what am I actually going to do? So I'm going to use gradient descent. The goal is to make the most accurate model possible. So we're going to try to pick the values of beta which are going to minimize the error, and like I said, we're doing that with gradient descent. So I did some research online about how to go about this, and it recommended 70% of the data to be allocated for training data and 30% for testing data. So all that means is that we're going to come up with the model using the data from training, and once we have our model solid, we're going to try it on the testing data, and if all goes well, it should work just as well on the testing data as it did on the training data. Lastly, we're going to standardize the data, which basically just means to put the data on a level playing field. So the method I used of standardizing the data is called z-scoring, and this is the calculation. It's pretty straightforward. Score, basically, this part is just meaning the data point. So you find the mean of all the data, and then you do your individual point minus the mean over the standard deviation. And it's important to note that when we're doing the standardization of the training data, we use the mean and standard deviation when we do the z-scoring of the testing data, we use the mean and standard deviation of the training data. the goal, what we're trying to do is minimize the error. We're trying to make our model as accurate as possible. The way you do this is, well, at least to begin with, you have to treat error as a function, come up with some sort of function to represent the error, because once you have a function, you can do all sorts of things with it. We want to look at how error changes when our inputs change, and then in turn use that information to minimize the error. So error can be represented by the variable r, which means residual, and the way you find it is by taking the actual value and subtracting what you thought the value was going to be, and what's left over is the residual, the error. So in the last slide I was talking about making a function for error, and in my case this is the function that I used. It's called mean squared error, and it's pretty self-explanatory. You just find the residual for the data point, square it, do that for all the data points, sum them, and then divide by how many data points you had, and get the mean squared error. And the reason I chose mean squared error is, like I said, you want error as a function, and so r squared makes a parabola, and parabolas are easy to work with when doing gradient descent. They're optimal. Also, because r is squared and it represents the error, squaring the error makes it blow up, and it makes it more punitive. So if you were to have absolute error, where it's linear, and your error was 4, then the error is just 4. If you have your squared error, if your error was 4, your error is all of a sudden now 16. So it just trains your model better. It is more susceptible to outliers, but in my case, there's no outliers because this data is already, this data is very well behaved. We want to look at how the error changes when we change our inputs, and that's what this represents. So since there's 5 inputs, we're going to make a gradient function, and it's going to have 5 terms, and it's going to be how the mean squared error changes with each beta. So mean squared error is just a number, and its inputs are our betas. So this function tells us in which direction we need to go to have the biggest resultant change. So we want to minimize our error, and our error is a parabola. So we want to know in which direction we need to go down that parabola to get to the bottom the quickest. So that tells us the direction, but we also want to know how big our step is going to be. So we introduce a new variable called alpha, and this is the quote-unquote learning rate. So it's like how fast are we going, how fast are we learning, how fast is our betas changing. So a higher beta rate means a higher learning rate means a bigger jump. So this is the culmination of all of this. This is like an iterative equation, so you run this over and over and over and over. You take your values of beta, you plug them into the gradient function, and then you multiply by the learning rate, and then you subtract that by, or you take your original beta and then you subtract that, and that will give you a new beta. And at first the jump is going to be huge between the new and old, but the more times you run the process, the smaller the difference is going to be until they're almost identical, and that's what you're going for, because that tells you that you've minimized the error. Alright, this is the moment that everyone's been waiting for. So on the left hand side, this is the raw data. On the right hand side, this is the standardized data. Here we have the mean and standard deviation for the data, which is obviously used when I standardized it. And then here is, here's where it went down. So this ended up being the final equation I got, and the error was about $11, and this is our MSE, so it's the square root of our MSE, just to put it back into a readable number. And one important thing to note about this equation is the coefficient on volume is almost 0, and I guarantee that if we had left it keeping going, it probably would have just gotten smaller and smaller and smaller. What this means is that volume is like essentially totally irrelevant in the calculation, which I found to be pretty interesting. This is a graph of the predicted versus actual close, and you can see that the model is pretty good. I'm honestly really proud of my model, and I had so much fun training it. Like, it was such a cool experience for me. So this is kind of some total sadness. I should have done this before I trained the model, but I waited until after because I was just not being very smart. It's kind of obvious when you think about it, but I just didn't think about it, and I didn't compute it either. But you can see in the correlation matrix that the variables are highly correlated. They pretty much move with one another. What this means is that it means that our predictions are highly unstable. Essentially, if you imagine the betas, if the inputs are the same, then the betas are interchangeable almost. So it kind of means that we can't draw any great conclusions from my model, which is sad, but at the end of the day, I'm still really happy with what I was able to produce, and the process was good. So I know that if I found some different data, I could still repeat the process and come up with some great results. So all in all, I'm not too disappointed or anything. Thank you for watching. I hope you enjoyed my project. I know I rambled a lot and explained a lot of the equations. My actual hard math is going to be more on the paper, but I did focus on the video presentation more than the paper, so I hope that it's good enough, and yeah, thank you for watching. I hope you enjoyed.